So let's look at some of the updates I've made to this CPU. So first of all, if we get into the ALU, you can see that I've expanded the ALU. So rather than having a 3x8 decoder, I've got a 4x16. So this gives us 16 possible functions that we can generate within the ALU. And you can see I've added a few extra here. So I've got the increment, the decrement, a multiplication, division, we've got addition and subtraction. Of course, we've already got an addition down here. So I may well either replace this addition or get rid of this addition. Either way, we've got options and we've still got space to add in another couple of functions if we want to add those in. So that's a very simple change, and again it's not been completed yet because I haven't added in the instructions for these multiplication and division quite yet, but I will do that in the next few days. So that's the first main difference in the CPU. Now, most of the changes we made have been made in the control section. So in this control unit here, I've put some of the circuitry that was outside the counter inside it, and it just makes it a little bit neater. So for example, I've added in this section here which chooses the fetch and the enable, and I've added the little execute clock here inside this as well. So it just makes it a little bit tidier on that top level. And I've done the same with the microcoded ROM. I took the components here, which were all sitting outside at the next level up, and I've just put them inside this box. Now also, apologies here because you don't have my image. I usually talk with my webcam in here, but for some reason it's not working tonight, so I'll try and get that fixed for the next video. Now I'll try to explain my process here and the changes that I've made here within the control unit. We still have the fetch, which is hardwired. We have the 16 possible steps that we can generate here for the execute. Now I've placed the sets and enables so that they all match up. So you can see that it runs R0, 1, 2, 3, floating point unit, LR, stack, flag, and it runs exactly the same up this side here as well. Now another thing I've done is, previously we had an option for RA, RB enabled, and then only RB set. So I've changed that so that we can both generate RA and RB set. So that's the extra little bit I've added in, and also the RA and RB enable. And I've done that down here, and that's this little section here. So previously we had this little block here, and I've just copied it over to the RB section, and this gives us our RA and RB set. So it means that we're going to have the this control by the line 30 and 31, which is really just our Reg A enable and Reg B enable, and also these two outputs here. So all four of these come from the microcoded control unit. So this gives us our RA set and RB set. So I just finished this off tonight. That's why we've still got a few of the extra bits of information here, which I'll probably get rid of. But the main point about this here now is I've really generated the best of both worlds. I have the microcoded section here, which will control all of the sets and all of the enables, and also the other outputs here to the adder and subtractor. So all the other outputs to, for example, the ALU. Now, I've also generated these two decoders, and I've extended the number of bits that we use here for our reg A and reg B. So remember, reg B are the 4 least significant bits here now, and the reg A are the next 4 bits. So that means that if we've got 4 bits, we've got a possible of 16 outputs we can generate here with a decoder. So if we can generate 16 outputs with a decoder, it means that we've got access to all of these sets because we've only got 14 of them. So you can see here we've got a reg A, reg B set, and I've got access to each of them. But I've also got access to each of them via the microcoded control unit. So it means in effect you can kind of think about this as we've got control over all the sets and the enables from the microcoded control unit, which we need because the microcoded control unit is clocked, and as the clock changes, all the sets and the enables change. So for example, if we were doing a data command, it's going to have 4 different lines, and each of those lines we're going to have different enable and set lines go high. So you may be wondering then, why bother adding the extra complexity of having the option of controlling these sets and the enables via the reg A and the reg B? Well, we know here that the 8 lowest bits here are going to control these 8 bits for our reg A and our reg B. So whenever an instruction comes in, these remain fixed throughout the lifetime of that instruction. They don't change. Okay, they're static. But these values up here from the microcoded control unit are not static, if you like. They're dynamic. They change with each clock pulse. So it means that we've got one option here of a set and an enable. And we can choose to use that option for our set and our enable at one point throughout the microcoded instruction. Now, the reason for doing this, and it might not be obvious from looking at this, but the reason for doing this is that it makes the opcode a lot simpler. And you can see that if I open up a spreadsheet here, which I used. Now in this spreadsheet, I used this in order to generate the output for our microcoded control unit and also a little compression ROM as well. And whenever I generated for example, the push commands, if I was pushing a register onto the stack, I would have a 6-bit opcode. But then if I decided I wanted to push the instruction address register, for example, onto the stack, then I needed another 6-bit opcode, because the functions or the lines here for pushing the instruction address register are slightly different from pushing the register R0. In fact, they're only a difference in one value, but they're still different. So I needed another opcode for it. And if I wanted to push any other register, I needed to have another opcode for that as well. So I actually did this and ended up generating about 12 different opcodes in order to push all of the values that I wanted onto the stack. Now that's not really the way I wanted to do it. What I wanted to do was just have one opcode, and then the value you wanted to push onto the stack would be determined by the instruction, and it would be determined by either the value over RA or the value over RB. And that's what this extra section here does. It allows us to push or pop or load or store in a very wide variety of ways. So previously, for example, if I took the data command only worked with register R0, 1, 2 and 3. But now as it stands, with this setup here, the data command will allow us to operate not only with these registers here, but with every other register that has got a set and an enable. So it makes the control unit here a very generalized control unit, which is a good thing for a learning process. It means we can generate lots of different instructions. Of course, lots of instructions are actually of no value at all, but it doesn't matter. It just means that we can generate as many different instructions as we happen to require. And I actually created another spreadsheet here in order to generate those instructions. So if I will zoom in and I'll show you what I mean with this. So we have our 8 outputs here. So this is a reg A. So that's the 4 lines that we've seen here. So that's these 4 lines. And we have a reg B, which is these 4 lines. So that gives us 8 lines altogether. So if we generate every single possibility of these 8 lines, there's going to be 256 possibilities. So I've just generated every single one of them. And that's them all there. Now, of course, this option of 256 is going to be available for each of the individual commands. So the push command, which has got a 6-bit opcode, is going to have these 256 possible combinations available to it. And also the data command will have all these 256 available to it. And so will the add command. And every single command that we generate, every opcode that we generate, will have these 256 possible connections available to it. So this makes it we can generate a really neat and a very general control register that will allow us to generate just about any instruction you care to think about. And that's really what we want to be able to do. We want to be able to generate lots of instructions, to test this out, to try different instructions and see how they work. And that's exactly what I've started doing with this. So for example, if I was to look at this here, you can see here that this A and B just stands for register A and register B. So this register A is going to have 16 possible values for our R out. Okay, now there's 2 of them that don't get used. And we can see here that obviously there's 2 that don't get used because we have the 2 values here. It only goes up to 14. Then there's 2 don't get used, so that's 15 and 16. So we have those 16 possible values for our R0. So these values for our R0 can connect to another 16 values for our B register, and that's this register here. And you can see that this register here, it runs R0, 1, 2, 3, floating point unit, LR, stack, flag, just exactly the same as it does here within the control unit. Now we repeat that for our R1. So we're really saying that R0 can connect to any of these, R1 can connect to any of these, R2 can connect, R3 can connect to any, R4, the floating point unit, the LR, which we're still to get through, I've not talked about this so far, the stack as well can connect to any of these flags. So every combination of connections between all of our registers and the entire CPU can get connected to every other one. And you can see here that if I, for example, was to do a data connection, a data instruction. So I'll clip out of this. We've got a data instruction. Or in fact, it's probably better if I use the stack. So if I was to go in and say I wanted to, in fact, let's see if I've a push instruction. I don't know if I've got all the push instructions available here. I only just worked on this tonight, so I don't have all of these available here at the moment. Maybe talk about just about the data instruction then. So if I had the data instruction, now the data instruction allows you to move the next 16 bits into a register. So let's say I wanted the data instruction. Previously I worked with data R0, R1, R2 and R3 only. So I could only move data into each of these registers. But now with this setup, I've got the option of moving that data into the floating point unit or the LR or the stack or the flags or any other register using this data instruction. And that makes the CPU really very general in its makeup, and it allows us to generate lots of different instructions. Now it's hard to see obviously from this, and you need to give it a little go yourself, and of course whenever the course is finished it will be available to you to go and mess about with this yourself, and I'll have updated all of the rest of this with all of the commands. But as an example here, let's go in and we'll open up the top level, and we can see I'll just run the simple command that's already available there. So I'll just put the end command here, which now is 700. So all this is going to do just now is put the value FFF0 into the stack, and the stack's given by this here. Okay, so the 02 is going to be the data command. So that's the first 8, that's the top 8 bits of our 16-bit instruction. And then the D6 gives us the bottom 8 bits, and that tells us whereabouts we're going to move the value FFF to. And then the next instruction here is going to be the jump instruction, which tells it to jump to this address here, and the program really just ends at that point, so it doesn't really do anything. But we'll work our way through it just now and we'll show you what I mean. So if I was to start this here, we'll get in and reset it. Okay, I'll probably have to go back in here and stick in the 700. So if we were to run through the simulation here, you can see that we're going to go, going to drag out the 2D6, and you can see when we begin, I'll actually go through another couple of commands here. So when we head in, you'll see that in here it's stuck in the opcode. Okay, so this is the opcode here, and the 6 bits here are going to choose the position that we require within the microcoded control unit for the opcode. But the 4 bits here are going to come from reg A, and another 4 bits are going to be our reg B, and this is in effect the values that are put in by the user as part of the instruction. And it's going to tell it to move the data into the stack, and you can see that we're going to have the RA and RB set and enable values are going to go high as required in order to generate this code or this instruction. Now I don't want to talk through every facet of this because it's just going to take too long. but we'll drop in and we'll have a look at some of it. So let's say we're at stage 2 here. You can just about make this out as a little green dot. So we're actually at stage 2 here of the counter. We get into the counter, you'll see that we're actually at stage 5, which is actually in effect stage 1, 2 of the counter for the execute cycle. So when we're at that stage 2, if we drop down into the microcoded, well, leave it at that point at the moment, you can see here that we're going to have the reg A is going to be set. So we come down here, reg A set, so that's reg A sets, this one is set. So it means that it's going to be passing from reg A, which is this one here, and it's going to be passing the set value down here. So that's the reg A, reg B set, and then you see the set value get passed down here, and it's choosing this value here because that's what we've told it to do from the 4 values here, 1, 1, 0, 1. And we've told it to come up and choose the stack. Okay, so that's forcing it to choose the stack here. So you can see we're using partly the instruction set here from reg A and reg B, and we're also using the value from the output here, which is the output of the microcoded control unit, and it is choosing the control enabled. And we're just at the second part of this particular instruction, which is the data instruction. So this is a good point here where you can see that we're both using the, if you like, the hardwired section here, and we're using the microcoded control unit. So we're using both of them in order to make the control unit as general as possible. So if I continue with this, you'll just see that it works through the process here. It's stuck F0 into the stack pointer, so that sets up the stack. It then goes to the jump command. The jump command pulls out address 8000. It jumps to the ROM, and the ROM has just got the end command, which is just 70. So it's not doing very much, but it just shows that these are the ones I've worked through so far and coded in. So I'll work through the rest of the values within the spreadsheet, and I'll generate the rest of the opcodes that we require. And it makes it an awful lot easier using this generalized control unit in order to generate whatever opcodes we happen to want. So a difficult one to kind of understand, but whenever I finish the entire course here within YouTube, the full course will be available to you, and you'll be able to use all of the tools that I have here, and you'll be able to download all of the simulations as well. So that's all for this video. Thank you for listening. I'll get you on the next video. Goodbye.